Hey everybody, this video will go over some of the most missed problems from the quizzes that we did last week. We're starting with this one, which turned out to be the most missed. We're talking about a basketball, which is 1 kilogram that's falling, and it hits the ground with a velocity of 7 meters per second. And then it bounces back up. And when it bounces back up, it still weighs 1 kilogram, but is moving at 3 meters per second. And we know that when it was in contact with the ground, the force was, somehow we know the force was 20 newtons, right? So what we're trying to figure out is how long was it in contact with the ground? What we can talk about is momentum. The momentum before is equal to mass times velocity. So 1 times 7, right? And so that's 7 kilogram meters per second. And the momentum after is 3. 1 times 3. 1 kilogram times 3 meters per second. So that's 3 kilogram meters per second. And so then we could talk about the change in momentum is what's the difference in momentum, which is 4 kilogram meters per second, right? It was at 4, now it was at 7, then at 4. It's a change in 7 and 3, which is a change in 4. Change in momentum is also known as impulse, and we know that impulse equals force times time. And so the change in momentum was 4 kilogram meters per second. We were given that the force was 20 newtons, and what we want to know is how long was it in contact. So we have this equation. We would divide both sides by 20 kilogram meters per second over newtons, which are kilogram meters per second squared. And if you simplify this out, you're going to get 1/5 second, right? Because the kilograms cancel, the meters cancel, 1 second cancel that second, and then it comes to the top. And so you have 1/5 of a second, which is the same as 0.2 seconds. All right, so that's that one. We get the next one. Okay, next question said, which free body diagram is correct for a car being pulled at a constant velocity? What you have to understand is that if it's constant velocity, that means the acceleration is 0, right? A constant velocity means there is no acceleration. If there is no acceleration, that means we're talking about inertia, right? An object in motion will stay in motion unless acted upon by an unbalanced force. So it's still possible that a force is acting on this car, but what's true about it is the forces must be balanced, right? And so we know there's a force being acted on it because it says it's being pulled, right? So what we know is, like, if our car is here, let's make this our car, we know that gravity is here, right? Here's the force due to gravity, and the force due to gravity should be equal to the normal force, so these two arrows should have the same direction. We know the car is being pulled, right? So we know there is this applied force in this direction if it's being pulled to the right. Now, if this were just the case, then this car would be accelerating because this is not in equilibrium, right? The net force is not 0. There's a net force to the right. And so the net force would be positive something, and this thing would start accelerating, going faster and faster, which means it's not moving at a constant velocity. So in order for it to be a constant velocity, there must be opposite force here, which is going to be force of friction that's stopping the car from accelerating, and that force of friction should be equal to the force of applied force so that it remains in motion at a constant velocity. Right, so you can see the one that does that best is here, where the arrows are the same size going up and going down, which is what's important, right? And it can't be A. Nobody chose that, but it can't be B because that would mean it's accelerating. It can't be C because also this arrow is bigger, which means it would be accelerating. And if it was E, this car would be slowing down because the friction would be greater than the applied force, right? So it's got to be D. All right, this is our next most missed question, and the reason I think it was most missed is it was a mistake. I'm not sure, like, I don't really understand what happened with these numbers, but because you can see in the diagram it's 1, 2, 3, and 4. He wants to know where is the maximum kinetic energy. Well, the kinetic energy is maximum at the lowest point. Here the potential energy is max, and there is no kinetic energy until it starts moving. Here it has potential and kinetic energy, down here, because it's on the ground, right, it's as far down as it goes, the potential energy is minimum and the kinetic energy is maximum. And then as it starts to go up this hill, it starts losing potential energy. Sorry, it starts losing kinetic energy, converting kinetic energy into potential energy. So the maximum kinetic energy occurs at 3, which, that's probably why you guys said this. I'm not sure why. I don't know who's picking 7 because it's not on there. But the correct answer is at 3. That's up there. So sorry for these weird answer choices. Hopefully that clears that up. Okay, next one says, from what height must a 20 kilogram hammer fall under 600 joules on a stake being driven into a ground? So imagine here's the ground. Let's make this our stake. And basically what we're going to do is we're just going to drop a hammer on it, right? So here's our hammer. We're just going to drop it down. We want 600 joules of work, right? So we know that work equals force times displacement. So in this case, we know that the work should be 600 joules. And we want to know, okay, what's the force times the displacement? What we can also think about is we need 600 joules of energy to be done, right? Assuming there's no friction here, because friction might slow this down. Oh no, never mind. We just need to do 600 joules of work. So basically we want to know, well, at what height will we have potential energy of 600 joules? And so basically we want to know, when will our potential energy be 600 joules? And we know that potential energy on Earth is the mass of the object times Earth's gravity times the height that the object is off the ground, right? And we know some of these things, right? We know that the mass is 20. We know the gravity is 9.81. We don't know the height, so we're going to solve for height, right? And if you do 600 divided by 20 times 9.1, let me do this real quick. 600 divided by 20 times 9.81. We get 3.058, right? So this height should be 3.058, which rounds up to 3.06. All right. Okay, next one we're talking about car accelerating, and we're looking for power output. It's important to remember that power is equal to work over time, right? A power is how much work you can do in a certain amount of time. So power equals work over time. So remember we talked about math problems. How many math problems can you do in a certain amount of time is going to be what power talks about. Work, we also know that work is force times displacement. And so we also know that, so let's just start with some things. We know that force then is also mass times acceleration. So we could convert power into this equation, mass times acceleration times displacement. And this might need to be converted into something else in a second. So let's just put in what we know. We know the mass. We know that he starts at 0 and accelerates to 40 in 1 minute. So that's going to tell us our acceleration, right? Our acceleration is basically v final minus v initial over the change in time. So this is 40 minus 0 over 1. So the acceleration is 40 meters per second squared. Yeah, so we could try to put that in here, and we would get power is the mass 1120. The acceleration is 40 meters per second squared. This is kilograms. The displacement we don't know yet, and the time is 1 second. Right? So the problem with this is we have two unknowns, right? We have a displacement and a power that are unknown. So one other way we can think about this is if you remember work, another definition of work is change in kinetic energy, right? So work and change in kinetic energy is the same thing. So if we think about, okay, how much kinetic energy did he have when he started? Well, he was moving 0, so that means 0 kinetic energy. And how much kinetic energy did he have when he ended? Well, 40, so kinetic energy is 1/2 mass times velocity squared. So his final kinetic energy is 1/2 times 1120 times his velocity squared. Let's get that number. 0.5 times 1120 times 40 squared gives you, hey now, we get, when we do this equation, when we put it all in, we get 896,000 joules. So that's our work. And so now we can actually say, okay, well, power is 896,000 over 1, right? So that's our power, which is why it is this. Just so you know, this is not part of this problem, but you could go back to this and you could figure out your displacement now, right? So you could actually plug in this, you could plug in this 896,000 into this equation that we had down here. And you could solve for your displacement, and you would know, you know, how far this thing went in that given time period. I guess we can do that real quick. We divide by you get 20. You get a displacement of 20. You could then also, you know that work equals force times displacement. You could then know that this is 896,000 equals force times displacement is 20. You can figure out the force, right, by dividing both sides by 20. And you can see how, like, just by knowing certain things, you can then figure out the rest of the stuff if you were asked to. Okay, next one is this conceptual question. A light plastic cart and a heavy steel cart are both pushed with the same force at a distance of 1 meter. So you want to think, okay, I have a force and I have a displacement. Well, that's basically work, right? Starting for rest, after the force is removed, the kinetic energy of the light plastic cart is blank of the heavy steel cart, right? So notice here, there's no mass involved, right? I mean, force is mass times acceleration, but it's saying the force is the same, right? So we're saying that the work on the first cart is equal to the work on the second cart. And so what that means is that the total energy given to that cart will be the same, right? Which means even though that little cart there is going to be moving much faster, that's fine, right? Because of the weight, the mass, the extra mass in the heavy cart, that means the heavy cart still has the same amount of kinetic energy, even though it's moving slower because its mass is bigger, right? So they should have the same kinetic energy because the same amount of work was done. Okay, so those were the most missed questions. The other ones, some people still miss them, but if you have specific questions about those ones, just go ahead and reach out to me, and I'll make you a video or something. You have another thing coming up, so please reach out with questions.